Today we are going to discuss one more important topic in quantum mechanics, that is the time-independent perturbation theory. Time-independent perturbation theory is a very important theory in quantum mechanics, and it is a basis of many important phenomena observed in quantum mechanics. So now we come to the first slide. So before understanding what is perturbation and why perturbation is needed, let me come to a small story that a group of closed friends enjoying party and fun. So here the picture is shown. The friends are enjoying party and fun. But one friend faces difficult situation in life. So one friend is sad and he is facing difficult situation. So it happens to us also. So in party and fun, a lot of friends are there. But whenever difficult situation comes, only few are remaining. Others, they go away. So one friend is remaining with him and he is helping the friend who is under difficulties. So some friends remain with the troubled friend and some friends, they move away. That is the normal situation taking place in a society. Now, why perturbation is important? Small difficulty in a life is helpful to identify the true friends. If difficulty was not there, then we would feel that all friends are equal and they are good friends, true friends. But when small difficulty came in life, only few friends they remain with us and other friends they move away. So we can identify who are the in real sense true friends and other friends are just for a party and fun. So difficulty can give idea what is in the minds of our friends, what they think, whether they are helping in nature or they are just for a party and fun. So small difficulty in a life is helpful to identify the surrounding situation. So similarly, we want to see that a perturbation, a small distortion or perturbation in a microscopic system, maybe atom or molecule, help us to identify inner detail or interactions. So similarly, a small difficulty in life that helps us to identify true friend or just a casual friend for party and fun. We can identify easily. Similarly, the small perturbation can help us to understand the inner detail or interactions in a microscopic system. And here the picture of an atom is shown in a laughing, and here the atom is shown in a cartoon in a sad face. So we can see that how atom reacts with the perturbation, and from that we can identify what is happening inside the atom. So it is a very important theory. Now, significance of perturbation theory. In quantum mechanics, perturbation theory is a set of approximation schemes directly related to mathematical perturbation for describing a complicated quantum system in terms of simpler one. The idea to start with a simple system for which a mathematical solution is known and add additional perturbing Hamiltonian representing a weak disturbance to the system. If the disturbance is not too large, the various physical quantities associated with the perturbed systems, for example, energy level and eigenstates, can be expressed as corrections to those of the simple system. These corrections, being small compared to the size of the quantities themselves, can be calculated using approximate method such as asymptotic series, and the complicated system can therefore be studied based on knowledge of the simpler one. In fact, it is describing a complicated unsolved system using a simple solvable system. So this is the significance of the perturbation theory. Now, perturbation theory, two different categories of perturbation theories are found. One is time independent one, which we are going to discuss today. Another one is time dependent. In the time independent perturbation, the perturbation is constant and does not change with time. So that is why it is called as a time independent one. The ideal examples are applying magnetic field or electric field. Applying magnetic field gives the Zeeman effect and applying electric field gives the Starck effect, and we are familiar with these two different effects. Now we come to understand the mathematical concept of time-independent perturbation theory. Suppose all the eigenvalues En and eigenfunctions Un forming a complete orthonormal set of Hamiltonian H0 of a given system. So it is something like a Schrodinger equation, H psi equal to E psi. So H0 is a Hamiltonian operator operating on Un, that is the eigenfunctions giving eigenvalue, again eigenfunction as it is. And forming an orthonormal set means delta Mn, when M and N are equal to 1, means equal to each other, then delta Mn is 1, and M and N are not equal to each other, then delta Mn is 0. So if the system is perturbed by the action of external field, the Hamiltonian changes to H. So instead of H0, it changes to H. So again, HV, WV. So H is a Hamiltonian, V is a eigenfunction. This is the eigenvalue, again eigenfunction, but that is the system under the perturbation or effect of external field. Now the Realist Schrodinger perturbation theory gives a systematic method of successive approximation to any perturbed eigenfunction V and eigenvalue W. We have already seen that eigenfunction V and eigenvalue W from the discrete part of spectrum in terms of unperturbed eigenfunctions Un and eigenvalue En. So Un and En are unperturbed eigenfunction and eigenvalue. V and W are perturbed eigenfunction and eigenvalue. So the Hamiltonian is now divided into perturbed and unperturbed Hamiltonian. So H is divided into two parts, H0 unperturbed Hamiltonian and H prime is a perturbed Hamiltonian. It is the general practice to show V and W in equation 2 in form of a power series in perturbation. If the perturbation is small, the successive terms becomes smaller and smaller. Usually, the first few terms of series are good enough for good approximation to V and W. So W can be expanded into power series. So summation 0 to infinity lambda raised to n W in bracket n. Similarly, V can be summation 0 to infinity lambda raised to n V of order n. So the term proportional to a particular power lambda raised to n in equation 4 in this equation are called the nth order terms. And in this term, the perturbation lambda h prime involves n times. So if n is equal to 2, then it is a second order. If n is equal to 1, then it is a first order. Now using equation 2, 3, and 4. So here h is equal to h0 lambda h prime. And that can be converted into, this is the VW HV0 lambda h prime V. And here, this can be represented as H0V, this bringing on the one side only, equating to 0. So lambda H prime V minus V W V equal to 0. And now we are putting the power series in this equation. And this term is H0 V 0th order HV1 lambda, then H0 V2 lambda square. Like this, the power series goes on. Then the second term is V0 power series term. Then V1 again lambda, the power series term, and similarly the last term. Now separating terms for different power of lambda. So the 0th order lambda, where there is no lambda, we have segregated into this one. Where first order lambda, only lambda is available, we have segregated into this. And when lambda square is available, then we have segregated into this term, and likewise for higher order of lambda. The above equation can be written for any small strength of perturbation for any lambda. And this happens only if the coefficients of each power of lambda vanishes or becomes 0. So this equation is equated to 0, and it is true only when the coefficient of lambda becomes 0, because lambda is a non-zero but small quantity. It is not zero, but a small quantity, but it is having a finite value. So this term should be zero, this term should be zero, this term should be zero, except lambda, and other terms become zero. So now we come to next slide. Now, having a zeroth order of lambda, we have segregated. First order of lambda, we have segregated. And there is a small printing mistake, so I have written once again. This is the second order for lambda. So where it is involves lambda square. Let us go to the previous slide. This is a lambda square, this is lambda, and zeroth order lambda. So we have segregated this term into different equations. Now W0 is one of the unperturbed eigenvalues. So W0 can be represented as EM. So it is unperturbed one because there is no perturbation there. Then V0 is an eigenfunction of H0 belonging to this eigenvalue. So if the unperturbed level EM is non-degenerate, then V0 is uniquely obtained. So if it is non-degenerate, then it is single valued or uniquely described, and this is known as equation number 11. If EM is degenerate, then eigenspace belonging to this level is spanned into different eigen functions like um1, um2 up to umr, and therefore V0 can be represented as alpha 1 to r a alpha umr, and here a1 a2 up to ar are constant. So we can represent for the degenerate as well as non-degenerate cases. Now we focus on the non-degenerate case. For solving the first and higher order perturbation equations, V1, V2 are expanded in terms of complete set of unperturbed wave function un. So V1 is represented as C1n un, V2 Cn2 un, and like that we can go up to the higher order terms, and we call it as equation 13. Now, the application of these expansions helps us to replace the operator H0 by its eigenvalues in equation 8 and 9. So here H0, Vs, S is a general order term, Cn as Un H0. And this can be represented as Cn as H0 U0 and Cn as En Un. So this is the eigenvalue for U0 and when we have a H0, and that is equation number 14. So this can be H0 eigenvalue can be obtained like this. The using equation 8, we can write H0 minus W0 V1 plus H prime V1 V0, and that is our equation number 8. This is equation number 8 for first order. Now we use that H1 opening the bracket. So H0 V1, W0 V1, and this bracket as it is. Now using equation number 14 to replace V1. And this is instead of Vs, we can write V1. So using equation number 14. And here Em is replaced by this, W0 is replaced by Em, and that is using equation number 10. So using equation number 10. So using two different equations, we have simplified. Now this can be further written by using the summation sign. So it is summation taken for n different states. So Cn1 En Un minus Em Cn1 Un, and here H prime minus W1 and V0. Again, we have used here that equation number 13 over here for writing Cn. So for equation number 13, we have written here the Cn. Now we can bifurcate into the summation taken for n, and here En Em, then Cn1 En common, un common. So Cn1 un common. So these things are common. So En minus Em, Cn1 minus un, and the second bracket is as it is. So it is equation number 15. Now, taking the scalar product of UK with equation number 14 and taking that UK UN is equal to delta Kn. So we are taking a scalar product of this equation. Now, scalar product means simply multiplying by UK. So we are multiplying by UK. And here we are using this equation number 11 to replace this V0. So again, go back and we have replaced V0, this equation V0 we have replaced. And using this equation, En minus Em, Cn1 UK UN, and here H prime minus W1 UK. We have replaced V0 by UM. And En minus Em, Cn1 delta Kn, because we have taken a multiplication of UK and UN, and both are orthonormal. So we are using delta Kn orthonormality sign. Again, here multiplication of UM and UK, both are orthonormal. So we are using that delta Km orthonormality property. So here En minus Em, Ck1, and if you take k equal to n, this delta Kn becomes 1, and n and k both are equal to each other. So you can write Ck1 instead of Cn1 because k and n both are equal to each other. And here it is H prime Km minus W1 delta Km. Now, what is H prime Km? We have defined over here. H prime Km is equal to UK H prime UM. So it is a multiplication in orthonormal property UK H prime UM. And it is called the matrix element of H prime between the states UK and UM. So this is represented as H prime Km. Now we come to the next slide. Now using 13 in equation number 9. So H0 minus W0 V2, H prime minus W1 V1 minus W2 V0 equal to 0. Now again, this is equation number 9, and we have rewritten equation number 9. Now opening the bracket H0 V2 and W0 V2, and this bracket as it is, and last term is V2 V0 equal to 0. Now we are using three different equations over here. Here we are using equation number 14 to simplify this. Here we are using equation number 10 to represent for W0. Here we are representing for H0 using equation 14. And V2 is represented by using equation 13. So we are replacing V2 by UN, and that is by using equation number 13. So three different equations are used for the first two terms. Now, multiplying with UK and using UK UN is equal to delta Kn orthonormality property. So this term is multiplied by UK. So each term is multiplied by UK. And again, here we have used equation number 13 for V1. And here we have used equation number 11, and that is for V0. So equation number 11 is used for V0, and equation number 13 is used for V1. And one can solve equation number 16 for V1 and CK1, and then use this in 17 and find W2 and CK2. So how we have obtained this? So particularly En minus Em, here En minus Em, CK2, because K is equal to N. And if you take K is equal to N, you can write, instead of N, you can write K. And using the orthonormality relation, if K is equal to N, then delta Kn is equal to 1. So En minus Em ck2 summation h prime kn. Now this is a particularly the matrix element minus w1 kn cn1. This is cn1 and w2 delta km because it is a multiplication between two orthonormal states uk and um. So we are writing delta km and that is equation number 17. Now we are coming to the first order perturbation. So we have two different equations. One is for the first order, another is for second order. Now obtaining from equation 16 for k is equal to m and delta km is equal to 1. So this is equation number 16. So ek minus em ck1 h prime km plus w1 delta km equal to 0. Now we are taking k equal to m. So this em becomes ek. So ek minus ek is 0. And here it is a multiplication between um and uk. So the matrix element becomes h prime kk because k is equal to m we have taken. And w1, k is equal to m. So delta kk again 1. So first term is 0. H prime kk minus w1 delta kk is 1 is equal to 0. So h prime kk is equal to w1 and that is equation number 18 and that gives the value of w1. So the first order change in the energy is simply the expectation value of perturbation taken with respect to the unperturbed wave function um. So this is unperturbed wave function um. Now for k is not equal to m. In this equation, we take another situation where k is not equal to m. So delta mn is equal to 0. Again, equation 16 becomes, so this is 16. So ek minus em ck1 h prime k m plus w1 delta km equal to 0. Now we are taking k is not equal to m. So ek and em will remain because they will not become 0. They are not equal to each other. This is ck1. Then h prime km because they are not equal to each other. Km are not equal to each other. The last term becomes 0 because delta km, k is not equal to m. So delta km becomes 0. So this can be simplified ek minus em ck1 h prime km. And from this we can find out the value of ck1 in form of minus h prime km divided by ek minus em. So this is the value and we have to now determine cm1. To find its value, to find we use the condition that the perturbed wave function v be normalized and taking v into the first order. So to find out the cm1, the condition is that we have to normalize the perturbed wave function. And for that, we assume that perturbed wave function is approximated um plus lambda cn1 un. So this is the first order because only in terms of lambda. Now, we further modify that v is equal to 1 plus lambda cm1 um, approximating for this. And second one is lambda cn1 un. So for um, we are writing this particular term. And in this case, for the second term, n is equal to m is avoided. So this is not taken. In this particular term, n equal to m is not taken. Now we come to the second slide. Now we are normalizing it. We know that normalization condition is that the modulus of coefficients square becomes 1. So here the modulus of coefficient, again modulus of coefficient square becomes 1. So this is the normalization condition. Keeping only the terms of the first order of lambda, because the second order terms are not complete without taking contribution from lambda square v2. So if we try to expand this, it is 1 plus 2 lambda cm1 plus lambda square Cm1 and the square equal to 1. Now, considering this, we can write 1 plus 2 lambda Cm1 because we are not involving the second order perturbation. So this is neglected because second order perturbation we are not considering, only the first. So it is 1 plus 2 lambda Cm1. Now this one goes on the right hand side, becomes 0. Ultimately, Cm1 is equal to 0. And that is equation number 22. In other way, one can write lambda Cm1 plus Cm1 star. This Cm2Cm, it is 1 plus lambda 2Cm. So actually it is 2Cm is divided into 2Cm is divided into Cm1 and Cm1 star and is equal to 0. So it is 2 lambda Cm1 equal to 0. But Cm1, 2Cm1 is written in terms of Cm1 and Cm1 star, its complex conjugate. Now, if you consider that Cm1 is equal to I alpha, then using equation 20, we can write V is approximately equal to 1 plus I alpha um plus this term. If you go to this equation, then we can write that 1 plus I alpha is approximated is equal to e to the power I alpha. And this is nothing but a phase factor. This is giving a phase factor in the wave function. Now, the usefulness of perturbation theory depends on the smallness of the change lambda v1 in the wave function, and which requires following condition. So for that, now we have to use equation number 13. We have to write v1 summation cn1 un. Now we know that v1 is equal to minus, we have to write the value of cn, and that is using equation number 13. So um is is h prime nm divided by en minus em. And in that case particularly, the lambda h prime nm, which is very, very less than en minus em. This is larger than lambda h prime nm. This is larger than lambda h prime nm. So h prime nm is in the numerator multiplied by lambda modulus, which is very, very less than en minus em. So this gives the criterion for the smallness of perturbation. The energy change lambda v1 equal to lambda h prime nm should be small compared to the spacing between em and its neighboring level. So em and its neighboring level is en. So the distance between the two levels is very much larger than this particular quantity. And this gives the criterion for the smallness of the perturbation, and which is written in a box, which is an important criterion. Now we come to the second order perturbation theory, which is slightly complicated than the first order perturbation theory. But first order is naturally a simple one. The second order is slightly complicated and equations are slightly bigger one. Now we come to the second order equation 17, and we can solve it for k equal to m using delta mn. So delta mn becomes 1. So this is equation number 17. We are rewriting for second order term. So it is ek minus em ck2 summation n h prime kn w1 delta kn cn1 w2 delta km equal to 0. Now we are writing for that em minus em because we are writing for k equal to m. So this becomes 0. And here h prime nm and w1 delta mn cn1 w2, because m k is equal to m, so delta mm becomes 1. So ultimately the first term is 0 and this term becomes 1. So h prime mn minus w1 delta mn cn1 minus w2, because delta mm becomes 1. And here we are considering that m is not equal to n. So ultimately, H prime my M Mn minus W1, and this M is not equal to N we have considered. So this delta Mn becomes 0. So H prime Mn minus W1, 0 multiplied by 0, Cn1 equal to W2. This is a printing mistake, so we are not focusing on that. And it is summation H prime, this term becomes 0, H prime Mn, the Cn1 equal to W2. Now, we are considering this equation and we have shown with the arrow. So this equation is 25, summation H prime Nm Cn1 equal to W2. Now, W2 is H prime Mn minus H prime Mn En minus Em. And we are taking K is equal to M and M is not equal to N. So if we take K is equal to M and M is not equal to N, if M is equal to N, this becomes 0 and becomes infinitely large. So it is not possible. So we are taking a condition M is not equal to N. So W2 is H prime Mn, H prime Mn, En minus En. Now here H prime is a self-adjoint Hamiltonian operator and its numerator of equation 26, numerator of equation 26 is not negative and takes the form. So W2 is equal to H prime Mn modulus square. Now, what is the self-adjoint Hamiltonian? So, self-adjoint Hamiltonian, usually the operator is shown by matrix. And in a matrix, row and columns are there. So, if H prime is Mn, so rows and columns are shown by Mn. If it is a self-adjoint, so then you interchange rows and columns and take a complex conjugate, then there is no difference. Both are same. So here Mn, here it becomes Nm, taken a complex conjugate in star, and there is no difference. So self-adjoint operators are defined like this. Now we come to the next slide. If the unperturbed state is the ground state, then En minus Em is equal to En minus E0 greater than 0. That's for all n. So it is unperturbed state is the ground state. So ground state is E0. And it is seen that W is negative. Writing equation 17 for K is not equal to M. So earlier the condition was K equal to M. Now we are putting the condition that K is not equal to M. So here the first bracket will remain because K is not equal to M. And here H prime Kn minus W1, and it is delta Kn Cn1 W2 delta Km equal to 0. That is equation 17. Now En minus Em Ck2 summation n H prime Kn, and here W1 Kn Cn1 W2 0 because K is not equal to M we have taken. So this delta Km becomes 0. So Ek minus Em Ck2 summation H prime Kn minus W1 delta An Cn1 equal to 0 because this term is equal to 0. Then we are writing for Ck2. So this is for Ck2. This term goes into the denominator. And we are taking it on the other side. So we are taking it the right hand side. So with the minus sign, it is preceding. So it is Ck2 is equal to minus summation H prime Kn minus W1 Kn Cn1, and in the denominator Ek minus Em. Now focusing on this, we are rewriting this equation once again. So Ck2 is equal to minus summation H prime Kn and Cn1, just opening the bracket, W2 Cn1 and delta Kn. Then denominator Ek minus Em. Now H prime Kn Cn1 minus W1 Ck1 because K is equal to N taken, and here K equal to N means delta Kk is ultimately 1. So it is ck2 equal to minus summation n h prime kn cn1 minus w1 ck1 divided by ek minus em. We call it equation number 27. So we have obtained the value of ck2. As we have done in our earlier case for the first order in equation 20, we do the normalization of v for this order, second order also. So in the second order, we have v approximately equal to um plus first order lambda v1 and lambda square v2, that is for the second order. As we have done earlier also, v is approximated as um is 1 plus lambda square cm2, because we are writing for this. And for the other higher order, it is lambda cn1 lambda square cn2 un. So that is for the higher order terms, because this is for one order, this is for another order. And we have considered that n is not equal to m, and we call it as equation number 28. As we have done in our earlier case, the normalization process is done. So the coefficient of this just preceding modulus square is equal to modulus square plus the coefficient preceding this un. This is again summation lambda cn1 plus lambda square cn2 modulus square. This coefficient modulus square, this coefficient modulus square is equal to 1. And that is normalization equation. And that is equation number 29. Now expanding 29. So just simple expansion of bracket. So we'll find this. In equation 29, the retaining only second order terms, because we are talking about the second order terms. So this can be retained, this can be retained, but other terms cannot be retained because this is lambda raised to 4, this is lambda raised to cube, again lambda raised to 4. So we cannot retain the other terms. Now cm, it is again 2 lambda square cm. It was earlier in the first order 2 lambda cm. Here it is 2 lambda square cm. So this term is written in terms of cm2 plus cm2 complex conjugate plus again this term, it is cn1 modulus square, because it is cn1 modulus square. We are just focusing on the lambda square terms only, and it is equal to 0, taking it to equal to 0. Now this condition determines the real part of cm2. The imaginary part can be included in em by redefining the phase factor and can be taken to 0. From equation 30, from this equation 30, we can write cm2 cm2 star, cm2 cm2 star, and therefore 2 cm2 is equal to minus, because these are equal to each other, so it becomes 2 cm2 and is equal to 0. So taking this on the other side, because lambda square, dividing this equation by lambda square, so this lambda square will go away, 0 divided by lambda square, again 0. So 2 cm2 is equal to minus modulus cn1 square. And from this we can write cm2 equal to cm2 star equal to minus 1/2 modulus cn1 square. And that is equation number 31. Now we are focusing on v2, second order, is summation ck2 uk, and putting the calculated values of cn1 and w1. So using the calculated values. Now v2 is equal to ck2 uk. Now using 27, we can put the values of this, and ck2 we have already obtained in equation number 27. So ek minus em summation h prime kn cn1 minus w1 ck1 uk. This uk is there. Now using equation number 19 for writing cn1 and ck1. So we are writing for that using equation number 19. So minus 1 divided by ek minus em summation H prime Kn Cn1. This is as it is. Now using equation number 19, so we have replaced is CK1 W1 and we have opened the bracket so that this EK minus EM is multiplied over here, EK minus EM, and minus minus becomes plus. Now in this step, we are using equation number 19. So this particular first term remains as it is, that EK minus EM, H prime Kn, Cn plus, Cn1 plus 1 divided by Ek minus Em. Now H prime mm and Ck1. Now we are using here this equation number 19. Now it is Nm, it is not mm. Now this can be further written that H prime Kn divided by En minus Em. And we are writing for Cn1. It is H prime Nm divided by En minus Em. And H prime Nm divided by Ek minus Em. This is H prime Nm. It is not mm. And Ck1, we are writing it is H prime Kn divided by Ek minus Em. So we are using equation number 19 and equation number 27. Let us go back that we have used equation number 19 and 27. This equation 19 and equation number 27, we have used this 27. Now, this can be further expanded and we'll notice that it is H prime Kn divided by Ek minus Em minus, we are writing for Cn1, H prime Nm divided by En minus Em. Again, this is H prime Nm. It's a printing mistake. It should be H prime Nm, not mm. Ek minus Em. And replacing this, it is H prime Kn Ek minus Em. Now, if we simplify, V2 is again summation over K, summation over N, because both the quantities are there. H prime Kn divided by Ek minus Em. Again, minus minus becomes plus, so H prime Nm divided by Ek minus Em. Here we will notice that H prime Nm and H prime Kn both are there. So in the numerator, both are there. And in the denominator, because this minus sign, when we open, this minus sign becomes plus. So Ek minus Em, again Ek minus Em. So taking Ek minus Em whole raised to square and Uk. So this is equation number 32. That is for the second order perturbation. So one can observe that the second order perturbation formula is more complicated than the first order formula. And it becomes more complicated for third and higher order terms. The magnitude becomes smaller and smaller. So we notice that first order formula was simple one. Second order formula is still complicated. Third and fourth order formulas are more and more complicated. And the value of the term becomes smaller and smaller. So the value becomes small, but the complication increases. Now we come to the importance of the first order perturbation theory or the time-independent perturbation theory. The time-independent perturbation theory finds applications to study one-dimensional harmonic oscillator, ground state of helium-like atom, diamagnetic susceptibility of helium-like atoms, Starck effect, Zeeman effect, hyperfine interaction, etc. So these are forming the applications of time-independent perturbation theory. Time-independent perturbation theory was proposed by Erwin Schrodinger, well-known name, Nobel Prize winner, and he proposed in 1926 this particular theory. Now I suggest for the further reading, the quantum mechanics by Matthews and Venkatesan, and another quantum mechanics by Wagmare. Now this is a beautiful photograph. This is the month of February. Usually the flower show takes place in Rajkot city. So this is one of the picture of the flower show in Rajkot city. And this is the moving on a beach enjoying the beach. Thank you so much. Thank you so much for patient hearing. Thank you so much. Thank you.